Picture the view from orbit, a serene, swirling marble of blue and white hanging in perfect silence against the infinite velvet of space. It's a vision of breathtaking beauty, one that has captured human imagination for generations, calling us outward with the promise of discovery and the allure of the unknown. Yet behind that awe-inspiring vista lies a stark and sobering truth. Space is not a welcoming frontier. It is one of the most hostile environments humanity has ever dared to enter, a vacuum of extremes, radiation, and isolation where the smallest oversight can lead to catastrophe. For every moment of wonder astronauts experience, there are countless dangers lying in wait, silent and unseen. Have you ever stopped to consider the real risks facing those who venture beyond our atmosphere, the hidden threats that could turn humanity's greatest adventure into a nightmare? We often celebrate the triumphs of space exploration, the moon landings, the rover missions, the stunning images from distant worlds. But behind these achievements are stories of courage in the face of overwhelming peril. Stories that remind us just how fragile human life becomes when we step off our pale blue dot. From cosmic radiation that silently damages DNA, to the psychological toll of endless isolation, to the simple but terrifying reality that there is no air to breathe, no pressure to hold our bodies together, no margin for error. Every mission into space is a delicate balance between ambition and survival, and the dangers are far more numerous and more sinister than many people realize. Today, we're pulling back the curtain on these hidden threats. We'll journey together through 25 terrifying dangers in space, risks that astronauts and future space travelers face every moment they spend beyond Earth's protection. Some of these hazards are physical, some are psychological, and some could challenge the very future of human space exploration. This isn't just a list of facts, it's an invitation to understand what it truly means to leave our world behind, the fears, the wonders, and the sobering realities that come with reaching for the stars. So settle in and open your mind to the unseen side of space, because what you're about to discover may forever change how you see the final frontier. Our journey into the hidden dangers of space begins with what is perhaps the most insidious threat of all. One that is completely undetectable by human senses, yet poses a profound risk to any mission beyond Earth's protective embrace: cosmic radiation. Unlike the dramatic perils we see in movies, this is a silent, invisible assault. It's a constant raining downpour of high-energy atomic nuclei and other particles screaming across the galaxy at nearly the speed of light. These aren't just a few stray particles, it's a torrential downpour, and our astronauts are directly in the storm. This radiation primarily comes from two terrifying sources. The first is our own sun, which during solar flares and coronal mass ejections can unleash catastrophic bursts of protons and other charged particles, events known as solar particle events. Think of these as the sun's tantrums, violent outbursts that can deliver a radiation dose capable of causing acute radiation sickness in a matter of hours if an astronaut is caught without sufficient warning or shelter. The second, even more formidable source are galactic cosmic rays. These are not rays at all, but rather the nuclei of atoms like iron and nickel that have been stripped of their electrons and accelerated to unimaginable speeds by distant supernova and black holes. Their energy is so immense that they can tear right through the hull of a spacecraft, through shielding, and straight through an astronaut's body. When one of these heavy, high-energy particles slams into a person, it doesn't just pass through cleanly. It shatters through cells and DNA like a microscopic freight train, causing complex and often irreparable damage. The cumulative effect of this bombardment is a significantly increased lifetime risk of developing cancer, along with potential damage to the central nervous system and even cognitive impairments that could jeopardize a mission's success. And this is the core of the problem. Our current shielding is almost laughably inadequate against this onslaught. the aluminum hulls of our spacecraft actually make the problem worse in some cases. When galactic cosmic rays hit aluminum, they can splinter, creating a secondary shower of even more particles inside the capsule, a phenomenon known as Bremsstrahlung radiation. It's like trying to stop a bullet with a pane of glass. The glass might stop the bullet, but the shards and fragments become a new, dangerous hazard. This is the terrifying calculation that makes a long-duration mission, like a trip to Mars, so perilous. A round trip to the Red Planet, estimated to take about 3 years, would expose a crew to radiation levels that could exceed an astronaut's entire career limit. They would essentially be soaking up a lifetime's worth of radiation in a single voyage, facing a 1 in 5 increased risk of dying from cancer later in life. This invisible killer remains one of the single greatest obstacles to humanity's dreams of becoming an interplanetary species, a constant, silent reminder that the universe is fundamentally hostile to life as we know it. While we're rightly focused on the invisible dangers from outside the spacecraft, an equally frightening transformation is happening inside the human body, a silent and systematic unraveling of our very physiology. This is the insidious reality of microgravity, an environment that feels like freedom but acts like a slow-acting poison, convincing our bodies they have become obsolete. From the very moment an astronaut enters weightlessness, their system begins to receive a dangerous message: you don't need to be strong here. Without the constant pull of gravity, the intricate biological systems that evolved over millions of years to support us against that force start to shut down, leading to a shocking rate of decay that threatens both the mission and the long-term health of the traveler. One of the most immediate and dramatic changes is the fluid shift. On Earth, gravity naturally pulls about 2/3 of our bodily fluids down into our legs and lower torso. In space, that fluid redistributes evenly, rushing upward toward the chest and head. Astronauts often experience puffy faces, congested sinuses, and thin, bird-like legs as their bodies adjust to this new normal. But this isn't just a cosmetic issue. This increased cranial pressure is now strongly linked to a serious and persistent problem: vision changes. The pressure pushes on the backs of the eyeballs, flattening them and often causing swelling of the optic nerve, a condition known as spaceflight-associated neuro-ocular syndrome, or SANS. Many astronauts return to Earth with permanently changed eyesight, requiring glasses after a lifetime of perfect vision, a permanent souvenir from their time in orbit. Yet the physical breakdown goes far deeper than fluid. Our skeletons, the very framework of our bodies, are dynamic living tissue that constantly remodels itself based on the stresses we place upon it. In the absence of gravity, the signal for bones to maintain their density simply vanishes. The body, in its ruthless efficiency, begins to leach calcium and other minerals, leading to a devastating loss of bone mass at a rate of 1 to 2% per month. To put that in perspective, a post-menopausal woman on Earth might lose 1 to 2% per year. An astronaut can lose that in a single month. This isn't uniform decay. It primarily targets the weight-bearing bones, the spine, pelvis, and legs, leaving them brittle and profoundly weakened, significantly raising the risk of fractures both during missions and long after returning home. Simultaneously, muscles wither away from disuse. Without the need to stand, walk, or even lift a limb against gravity, muscle mass melts off at an alarming speed, a condition known as atrophy. The anti-gravity muscles in the calves, back, and neck deteriorate first and fastest. Crew members on the International Space Station dedicate a minimum of 2 hours every single day to intense resistance and cardiovascular exercise just to fight back against this inevitable decline. They use advanced equipment like the ARD, the Advanced Resistive Exercise Device, which simulates weightlifting in microgravity. Without this grueling daily regimen, an astronaut could return to Earth after a 6-month mission too weak to even stand or walk, their muscles having been literally unlearned their most basic earthly functions. The cardiovascular system, our powerful internal pump, also falls victim to this lazy environment. The heart, no longer required to work against gravity to push blood up to the brain, becomes deconditioned and weaker, shrinking in mass. This cardiac atrophy reduces overall fitness and, combined with the fluid shift, can lead to a dangerous condition called orthostatic intolerance. Upon return to Earth, many astronauts find they cannot stand for more than a few minutes without feeling dizzy or fainting. Their hearts and blood vessels simply cannot adjust quickly enough to the renewed pull of gravity, turning the simple act of standing upright into a monumental challenge. The true testament to the severity of this decay is witnessed not in space but back on the ground in the grueling process of rehabilitation. Returning astronauts are often carried from their capsules, their bodies unable to support their own weight. They embark on a months-long journey of physical therapy to rebuild the bone density, muscle strength, and cardiovascular endurance that microgravity steadily stole from them. While much of the damage is reversible with time and intense effort, some changes, like the vision alterations and some bone loss, appear to be permanent. This comprehensive breakdown presents a daunting challenge for long-duration missions to Mars or beyond, where years spent in transit could leave a crew arriving at their destination as physiological invalids, too weak to perform the demanding tasks of exploration on a new world. But while our bodies struggle to adapt to the emptiness of space, that void is far from empty. It's a shooting gallery, and one of the most immediate and terrifying dangers comes from what we've left behind. Imagine a bullet traveling faster than any rifle shot, a speck of paint or a tiny shard of metal screaming through the void at 17,500 miles per hour. At that staggering velocity, even a fleck of paint carries the kinetic energy of a bowling ball dropped from a several-story building. This is the reality of space debris, a cloud of hypervelocity projectiles we have created that now encircles our planet, turning Earth's orbit into a perilous obstacle course for every satellite and spacecraft. This isn't just a hypothetical threat, it's a daily operational hazard. The International Space Station, our home in orbit, is wrapped in a specialized shield called Whipple shielding, designed to vaporize small particles on impact before they can penetrate the inner hull. But this is only effective for objects smaller than about 1 centimeter. Anything larger poses a catastrophic risk. The station's flight controllers are constantly on watch, tracking the thousands of human-made objects large enough to be catalogued. When a piece of debris is predicted to come within a certain threatening distance, a constantly evolving threshold known as the pizza box, for its rough dimensions around the station, Mission Control orders a predetermined debris avoidance maneuver. This involves firing the station's thrusters to gently boost the entire complex into a slightly higher, safer orbit. These maneuvers are not rare occurrences. They have become a regular part of space station life, a constant dance to avoid destruction. The danger was horrifyingly demonstrated in 2009, when a defunct Russian military satellite, Cosmos 2251, collided with an operational American communications satellite, Iridium 33, over Siberia. The impact, occurring at a combined speed of over 26,000 miles per hour, utterly obliterated both spacecraft, instantly creating thousands of new pieces of trackable debris and countless more smaller fragments. This single event increased the known debris population in low Earth orbit by a staggering 70% overnight. Each one of those new fragments became a potential weapon, capable of causing another collision and creating even more debris in a nightmarish domino effect. This scenario is the heart of a terrifying theory known as the Kessler syndrome, proposed by NASA scientist Donald Kessler in the late 1970s. It postulates a cascade failure where the density of objects in low Earth orbit becomes so high that collisions become inevitable. Each collision creates more debris, leading to more collisions, until entire orbital pathways are rendered unusable, shrouded in a swirling cloud of shrapnel that would make space travel and satellite operation impossibly dangerous for generations. We are already seeing the early signs of this cascade in certain orbital regimes. Every time a satellite is intentionally destroyed in an anti-satellite weapon test, or when an old rocket body unexpectedly explodes due to leftover fuel, we add more fuel to this potential fire. The problem is self-perpetuating and has no quick fix. There is no vacuum cleaner for space. The energy required to chase down and to orbit even a single piece of debris is enormous, and the engineering challenges are monumental. Some proposed solutions include harpoons, nets, and even lasers to nudge debris into decaying orbits, but these are still in their infancy. For now, the only strategy is avoidance and prevention, trying desperately not to make the problem worse while we navigate a minefield of our own creation. This invisible ring of garbage around our planet stands as a stark monument to our carelessness, a potentially permanent barrier that could one day trap us on Earth, prisoners behind a barrier of our own discarded technology. If you think the vacuum of space is a quiet, still place, think again. It is a realm of violent thermal extremes, a place where the very concept of a comfortable temperature doesn't just not exist, it's physically impossible. There is no air to gently convect heat away, no atmosphere to diffuse the sun's brutal rays or to trap warmth in the shadows. Space is the ultimate thermal vacuum, and every object within it is locked in a constant, desperate struggle between blistering heat and bone-chilling cold, often at the exact same time. This isn't a gentle gradient, it's a battlefield of absolutes. An astronaut on a spacewalk or a satellite orbiting the Earth can experience these insane swings in a matter of minutes, even seconds, simply by moving from sunlight into shadow. In direct, unfiltered sunlight, surfaces can be seared to temperatures exceeding 250 degrees Fahrenheit, hot enough to boil water and cause severe burns. Yet, just a few feet away, in the perpetual darkness of an orbital shadow, those same surfaces can plummet to 250 degrees below zero, a cold so profound it makes Antarctica feel like a summer day. This is a temperature differential of 500 degrees, and it's a relentless, daily reality just a few hundred miles above our heads. For the machines we send into this environment, this presents an engineering nightmare of the highest order. Metals, plastics, and composites all expand when heated and contract when cooled. Subject any material to these rapid, radical 500-degree swings multiple times per orbit, which for the International Space Station is 16 times a day, and you introduce immense mechanical stress. This constant expansion and contraction, called thermal cycling, is like repeatedly bending a paperclip back and forth. Eventually, the material fatigues. Seals can crack, wiring can become brittle and break, optical lenses can warp, and critical components can simply fail from the exhaustion of it all. Spacecraft are meticulously designed with sophisticated thermal control systems, a combination of reflective white coatings, insulating blankets, electrical heaters, and looping tubes of coolant, all working in a complex dance to keep the sensitive internal electronics within a narrow, survivable temperature range. It is a never-ending fight against the void's indifference. For the human beings working outside their spacecraft, this danger becomes terrifyingly personal. A spacesuit is in essence a personal spacecraft, and it faces the same thermal onslaught. The suit's outer layer is white to reflect the majority of the sun's intense heat, and it contains a network of water tubes woven into an undergarment to keep the astronaut cool. But the margins for error are vanishingly small. A malfunction in the cooling system could lead to an astronaut overheating within minutes, their body trapped inside a portable oven with no way to shed the excess heat. Conversely, if the suit's heaters were to fail while in shadow, the bitter cold could rapidly sap their body heat, leading to hypothermia. Every spacewalk is a carefully choreographed ballet timed to maximize efficiency while minimizing exposure to the most extreme thermal conditions, a testament to our ability to create a tiny, fragile island of habitability in a universe of hostile extremes. This challenge becomes even more pronounced near planets and moons with little to no atmosphere. On the Moon, the 2-week-long lunar day sees temperatures soar to 260 degrees Fahrenheit, while the ensuing 2-week-long night plunges to 280 degrees below zero. Any future lunar base will have to be engineered to withstand this incredible seesaw, a task that will require immense ingenuity and resources. The thermal vacuum of space is a silent, pervasive danger that never relents, constantly testing the limits of our technology and reminding us that in the endless expanse of the cosmos, finding a middle ground is the hardest battle of all. Yet beyond the physical assault on the body and the constant threat from outside the hull, there exists a more subtle, deeply personal danger that strikes at the very core of who we are. The profound psychological toll of isolation and confinement. We are an intrinsically social species, hardwired for connection to our planet, to our loved ones, and to the natural world. A long-duration space mission systematically severs every single one of those ties, placing astronauts in a position of existential loneliness unlike any experienced on Earth. They are living in a tiny metallic shell, hurtling through an endless black void, with the entire human race reduced to a small, glowing blue dot in the distance that grows fainter with every passing day. The habitat itself becomes a world of severe sensory deprivation. There is no weather, no change of seasons, no day-night cycle that isn't artificially manufactured. The constant hum of machinery replaces the sound of wind or rain. Meals are consumed from plastic pouches, and the air carries the persistent, sterile smell of recycled oxygen and electronics. This monotonous environment can lead to a state of lethargy and depression, where every day feels indistinguishable from the last. Astronauts have spoken about the Sunday feeling, a lingering sense of melancholy that comes from the relentless routine. A phenomenon familiar to anyone who has felt stuck in a rut, but amplified 1,000-fold by the knowledge that there is no stepping outside for a breath of fresh air or a change of scenery. Compounding this isolation is the inescapable confinement within incredibly close quarters. A crew on a mission to Mars would be living and working for 2 to 3 years in a volume of space smaller than the average suburban home with the same handful of people. There is no privacy, no personal space to retreat to when frustration builds. The smallest habit, the way someone chews their food, a particular laugh, a minor disagreement over procedure, can become a source of intense, simmering irritation. On Earth, we have the luxury of walking away from conflict. In space, there is literally nowhere to go. This pressure cooker environment forces crews to develop unprecedented levels of emotional regulation and conflict resolution skills, knowing that a single unchecked argument could jeopardize the entire mission. Simulations on Earth, like those conducted in the HIC's habitat in Hawaii or in remote Antarctic stations, have repeatedly shown that interpersonal conflicts, not technical failures, are the most significant threat to mission success. Perhaps one of the most paradoxical psychological phenomena experienced in space is the overview effect, a term coined by writer Frank White. This is not a danger in the traditional sense, but rather a profound and potentially destabilizing cognitive shift reported by many astronauts who view Earth from orbit. Seeing our planet as it truly is, a fragile, breathtakingly beautiful oasis of life suspended in the vast, empty blackness, can trigger an overwhelming sense of awe and universal connection. Borders vanish and the petty conflicts that consume humanity seem insignificant. While this sounds like a beautiful, unifying experience, its intensity can be deeply unsettling. Astronauts return changed, often struggling to reintegrate into a world that seems obsessed with trivialities they now perceive as meaningless. This cosmic perspective can create a form of existential whiplash, a permanent feeling of alienation from the very society they left behind, making the already difficult process of readjustment to earthly life even more complex. The strategies to combat these mental health challenges are as critical as those for fixing a broken oxygen generator. Mission Control employs rigorous psychological screening long before launch, but they also maintain constant, though delayed, communication. On a trip to Mars, a simple question and answer with a loved one could take over 40 minutes to make the round trip, turning a normal conversation into a frustrating exercise in patience. Crews are trained to be jacks of all trades, not just for practical reasons, but to maintain mental engagement and a sense of purpose. They follow strict schedules that include mandatory exercise, work cycles, and even virtual reality experiences of forests and beaches to stave off sensory starvation. The mental fortitude required to endure this combination of extreme isolation, claustrophobic confinement, and existential awe is immense. A reminder that the final frontier demands not just healthy bodies but resilient and deeply prepared minds. And if the spacecraft itself becomes compromised, the crew faces a threat so immediate and so absolute it defies comprehension: exposure to the pure vacuum of space. This is not a slow leak or a gradual loss of pressure. It is a catastrophic, explosive decompression, an event where the life-sustaining atmosphere inside a capsule or suit is violently ripped away into the void. The human body, evolved for life within the gentle embrace of Earth's atmosphere, is utterly unprepared for this reality. The physics of what happens next are as brutal as they are swift, a horrifying sequence of physiological failure. The first and most immediate effect is the expansion of gases within the body. The air in your lungs at a normal pressure one moment is suddenly desperate to equalize with the zero pressure outside. This can cause the lungs to rupture or suffer catastrophic damage if an astronaut were to make the fatal mistake of holding their breath. Simultaneously, the moisture on the surface of the eyes, tongue, and in the soft tissues of the mouth and nose would begin to boil. Not from heat, but from the lack of atmospheric pressure. At the top of Mount Everest, water boils at around 160 degrees Fahrenheit because of the low pressure. In a vacuum, the boiling point plummets to below the normal temperature of the human body. This means saliva on the tongue would actually start to bubble and vaporize at 98.6 degrees. Within 10 to 15 seconds, the brain is starved of oxygen. This is not because the victim has exhaled all the air, but because the vacuum actively pulls oxygen out of the blood. Consciousness vanishes almost instantly. Historical accounts from high-altitude testing and tragic accidents in vacuum chambers suggest that a person might have a mere 12 to 15 seconds of useful consciousness to recognize the emergency and attempt to save themselves, a nearly impossible task. After that brief window, blackout is certain. The body would swell, not explode as sometimes depicted in science fiction, but rather inflate to perhaps twice its normal size as water vapor forms under the skin. Circulation would fail completely as blood itself begins to bubble and vaporize in the major veins and arteries, a condition called embolism. The heart might continue to beat erratically for another minute or two, but without oxygenated blood reaching the brain, permanent damage and biological death would follow within minutes. It is a clinical, terrifyingly efficient end. The history of spaceflight is marked by chilling near misses that underscore this ever-present danger. In 1971, the crew of Soyuz 11, Georgy Dobrovolsky, Viktor Patsayev, and Vladislav Volkov, tragically lost their lives during re-entry not from the heat of atmospheric friction, but because a faulty pressure equalization valve opened prematurely while their capsule was still in a vacuum. They were found lifeless in their seats, having succumbed to suffocation before their vehicle ever touched the ground. This disaster led to the mandatory use of pressurized spacesuits during launch and re-entry for all future crews, a direct and sobering response to the lesson learned. This constant threat is why safety protocols surrounding pressure are so rigorous and redundantly designed. Spacesuits are marvels of engineering, essentially individualized spacecraft with their own life support, pressure systems, and emergency oxygen supplies. Vehicles are equipped with multiple, independent sealing mechanisms on hatches. Crews train relentlessly for decompression emergencies, drilling to don oxygen masks or seal a compromised module within seconds. Every launch, every spacewalk, every moment in orbit is conducted with the silent understanding that a single seal failure, a tiny micrometeorite puncture, or an errant piece of space debris could trigger this ultimate emergency. It is the most immediate and personal of space's many dangers, a reminder that the thin line between life and death in the cosmos is literally the thickness of a hull or a spacesuit fabric. While our fragile vessels and bodies contend with the silent threats of vacuum and debris, the sun itself can transform from a life-giving star into a sudden and violent adversary without a moment's notice. This is the danger of solar flares and coronal mass ejections, colossal eruptions on the sun's surface that hurl unimaginable amounts of energy and charged particles across the solar system. Think of the sun not as a constant, gentle ball of light, but as a turbulent, seething sphere of plasma, its magnetic fields twisting and knotting until they snap like overstretched rubber bands, releasing titanic bursts of radiation and matter. A single one of these solar storms can carry the power of millions of nuclear bombs detonating simultaneously, and it races outward at speeds that can exceed 1,000,000 miles per hour. A solar flare is the initial flash of intense X-ray and ultraviolet radiation that reaches Earth at the speed of light, taking just over 8 minutes to get here. This radiation blast can immediately disrupt radio communications across the entire sun-facing side of the planet and rapidly increase ionization in the upper atmosphere, degrading GPS signals and radio navigation. But the more insidious threat, especially for spacefarers, follows shortly after the coronal mass ejection. This is a massive cloud of billions of tons of solar plasma, embedded with a powerful magnetic field ejected from the sun's corona. Traveling at a slower but still staggering pace, this wave of high-energy protons can arrive anywhere from half an hour to several days later, depending on the storm's intensity. For astronauts, a direct hit from a major coronal mass ejection is a worst-case scenario. Outside the protective cocoon of Earth's magnetosphere, they would be exposed to an intense wave of particle radiation. Inside a spacecraft, they would receive a radiation dose equivalent to getting a full-body CT scan every single hour for the duration of the storm, which can last for days. This level of exposure would likely cause acute radiation sickness, with symptoms including severe nausea, vomiting, fatigue, and skin burns. A powerful enough event could deliver a lethal dose. The radiation doesn't just target the crew, it also attacks the ship's electronic brain. Energetic particles can slam into computer chips, causing bit flips, corrupting data and software, or even permanent damage, potentially crippling navigation, life support, and communication systems at the most critical moment. The terrifying reality of this threat was underscored by a historical near-miss. In August of 1972, right between the Apollo 16 and 17 moon missions, the Sun unleashed one of the most powerful solar storms ever recorded. Satellites recorded the event, and its effects were felt on Earth with widespread radio blackouts and auroras visible as far south as Spain. Had astronauts been on the lunar surface or in transit at that time, they would have been caught with nowhere to hide. The radiation levels would have been severe, if not fatal. This event serves as a stark reminder that our exploration plans are at the mercy of solar activity, a variable we cannot control. This ever-present danger necessitates a robust space weather forecasting system. Organizations like NASA, Goddard Space Flight Center, and the National Oceanic and Atmospheric Administration constantly monitor the Sun with a fleet of satellites like the Deep Space Climate Observatory and the Solar Dynamics Observatory. These watchful eyes provide crucial warnings, sometimes giving crews up to a few days' notice of an incoming storm. The primary defense strategy aboard the International Space Station is the use of a designated storm shelter. Astronauts retreat to a more heavily shielded part of the station, often a corridor lined with water bags and other supplies that provide additional protection against the incoming particles, buying them precious time to wait out the storm. For future missions to the Moon or Mars, this shielding challenge becomes paramount. Lunar or Martian habitats will need dedicated, heavily shielded safe rooms, perhaps buried under regolith for protection. Spacecraft designed for the long journey to Mars will similarly require a storm shelter, a central core surrounded by the ship's water and food supplies, which act as effective radiation barriers. The success of these deep space voyages will depend not just on propulsion and life support, but on our ability to predict the sun's fury and our ingenuity in building a temporary fortress against its wrath. But the dangers of space aren't just about what's out there waiting for us, they're also about what we might bring with us, or worse, bring back. This is the dual-edged sword of contamination, a risk that has planetary scientists and biologists up at night. It breaks down into two terrifying possibilities, each with its own apocalyptic potential. The first is forward contamination, the fear that we, as a species, could be the invasive species. Every spacecraft we send to another world is not perfectly sterile. It carries with it a microscopic zoo of Earth's hardiest bacteria, tucked away in circuits and crannies, having survived the brutal cleaning process and the vacuum of space. If these tiny Earthlings were to be deposited on a place like Mars, with its subsurface ice and potential habitable zones, they could potentially survive, multiply, and utterly overwhelm any nascent, fragile native ecosystem we are hoping to discover. We would forever lose the opportunity to study that world in its pristine, natural state, and worse, we might become the agent of an alien world's biological apocalypse, all by accident. The reverse scenario is the stuff of science fiction horror, and it's taken deadly seriously: back contamination. This is the fear that a sample return mission, or even an astronaut suit, could bring back a biological agent for which Earth's life has no defense. Our entire biosphere, every plant, animal, and human, has evolved with a shared biological history. Our immune systems recognize and combat threats based on a common biochemical language. An extraterrestrial microorganism, having evolved on a completely separate world along a different evolutionary path, might operate on a biology so alien that our bodies wouldn't even recognize it as a threat. It could be a perfect predator, a pathogen with no natural predators of its own, capable of wreaking havoc on a global scale. This isn't just paranoia, it's a central plot of Michael Crichton's The Andromeda Strain, a novel grounded in very real scientific concern. This is why NASA and other space agencies have entire offices dedicated to planetary protection. Their job is to be the protocol enforcers for the solar system, implementing incredibly strict sterilization procedures for outbound spacecraft. Components are baked in ovens, blasted with radiation, and cleaned with aggressive chemicals to reduce the microbial load to astonishingly low levels. For missions like the Viking landers that went to Mars specifically to search for life, the sterilization was so thorough the entire spacecraft was essentially baked in a giant oven for days. The upcoming Mars sample return mission represents the biggest planetary protection challenge in history. The plan is to bring physical samples of Martian rock and soil back to Earth, and the protocol for handling them is unlike anything ever attempted. The current design involves a multi-stage containment system. The samples will be sealed inside a robust container on Mars, launched into orbit around the planet, captured by an orbiting spacecraft, and then placed within yet another highly secure Earth entry capsule. Upon arrival, they won't be delivered to a standard lab. They will go to a biosafety level 4 facility, the highest containment level possible, the kind used for studying the most dangerous pathogens on Earth like Ebola and Marburg virus. Scientists will study the samples inside sealed glove boxes with multiple layers of redundancy to prevent any conceivable leak. The terrifying unknown at the heart of this caution is the nature of Mars itself. We know its soil is rich in perchlorate toxic salts that are destructive to life as we know it, but we don't know if Martian microorganisms, if they exist, might have evolved to not just tolerate these chemicals but perhaps even use them. A perchlorate-based biology would be truly alien, and its potential effects on Earth's ecosystems are impossible to predict. Opening that canister of Martian soil will be one of the most momentous and potentially risky scientific endeavors humanity has ever undertaken. It is the ultimate Pandora's box. We can only hope that if we open it, what we find inside is a scientific marvel and not a biological curse. Navigating the sprawling emptiness of space presents a challenge so fundamental we barely think of it on Earth, the simple act of not getting lost. Down here, we are spoiled by the constant, invisible guidance of the Global Positioning System, a network of satellites that blanket our planet, providing pinpoint location data to our phones and cars. But venture beyond low Earth orbit and that safety net vanishes instantly. There is no cosmic GPS, no road signs, no familiar landmarks against the infinite black backdrop. Every mission into deep space is a high-stakes exercise in celestial dead reckoning, a test of precision and redundancy where a single miscalculation or computer glitch could mean the difference between reaching a new world and drifting into the eternal void. One of the most immediate and disorienting shocks for deep space travel is the introduction of profound communication delays. Here in orbit, astronauts can talk to mission control in Houston with less than a second's delay, making real-time troubleshooting and guidance possible. But the speed of light, while fast, is not instantaneous across interplanetary distances. As a spacecraft journeys to Mars, the time for a signal to travel between the vessel and Earth grows longer and longer. At its average distance, a simple hello from Mars would take roughly 12.5 minutes to reach Earth, and the reply another 12.5 minutes to return. That's a total communications blackout of 25 minutes for a single exchange. You cannot ask a quick question, you cannot get immediate advice during an emergency. If an alarm sounds, the crew is utterly on their own. They must become their own mission control, diagnosing problems and executing solutions without any outside help, relying on manuals and their own training while knowing that the experts on Earth won't even hear about the problem for over a dozen minutes. This lag turns every decision into a monumental test of crew competence and nerve. To know where they are going, spacecraft rely on a suite of ingenious yet fallible tools. The most critical of these is the Star Tracker, a sophisticated camera that takes pictures of the star field around the spacecraft. It compares the pattern of stars it sees to a built-in celestial map, much like ancient mariners used the North Star but with digital precision. By locking onto known stars, the spacecraft can triangulate its exact orientation in space, ensuring its antenna is pointed at Earth and its engines are aimed in the correct direction for a course correction burn. But what happens if the Star Tracker gets confused? A piece of drifting debris could reflect sunlight into its lens, mimicking a star. A computer error could corrupt its internal catalog. If the spacecraft loses its celestial fix, it can become disoriented, tumbling blindly and potentially burning its engines in the wrong direction, accelerating itself further off course. This is why navigation is a constant process of cross-checking. Engineers on the ground use the Deep Space Network, a system of massive radio antennas in California, Spain, and Australia, to constantly ping the spacecraft. By precisely measuring the Doppler shift in the returning signal, the same effect that makes a siren change pitch as it passes by, they can calculate the spacecraft's velocity and distance with astounding accuracy. They combine this data with the spacecraft's own reported position from its star trackers to create a supremely accurate model of its trajectory. But this incredible precision is predicated on one terrifyingly simple assumption: that the computers handling these complex calculations do not fail. A corrupted software update, a radiation-induced bit flip, or a hardware malfunction could send wildly incorrect data to the guidance system. The story of Apollo 13 is a testament to human ingenuity, but it's also a stark warning. Their navigation computer failed, and the crew was forced to use the only fixed point they had, Earth's limb against the blackness of space, to manually align their crippled ship for a critical engine burn that would bring them home. Future crews may not have such a visible reference point. The ultimate nightmare scenario, the silent terror of deep space travel, is the possibility of a permanent navigation failure leading to a trajectory error that cannot be corrected. Imagine a small, unnoticed error in a course correction burn. The engines fire a few seconds too long or at an angle a fraction of a degree off. Initially, the deviation seems insignificant. But over the vast distances of interplanetary space, that tiny error is magnified exponentially. A millimeter off course at the start of a journey can mean missing the target by thousands of kilometers. If the error isn't caught in time, or if the spacecraft loses all power and propulsion before it can be fixed, the outcome is unthinkable. The vessel would simply continue on its new path, sailing past its intended planet or moon without ever getting captured by its gravity. It would become a permanent monument to human ambition, a silent tomb drifting endlessly through the interstellar void, its occupants forever lost to the infinite cold and darkness between the stars. This is the profound responsibility and existential risk of cosmic navigation. Every calculation must be perfect because in the unforgiving physics of space, there are no second chances and no roads to pull over and ask for directions. Fire presents a danger so counterintuitive and terrifying it defies all our earthly experience. On our planet, fire is a familiar, almost predictable force. Flames rise in a teardrop shape, drawn upward by the convection currents of hot, less dense air, carrying smoke and heat away from the fuel source. We have built our entire understanding of firefighting on this fundamental principle. But in the microgravity environment of space, every single one of those rules is turned upside down, and fire transforms into something far more sinister and unpredictable. Without gravity, there is no buoyancy, no up or down. Hot air does not rise and cold air does not sink. This means a flame has no reason to shape itself into a familiar cone. Instead, it becomes a ghostly, ethereal sphere, a hovering ball of blue and yellow that spreads in all directions with a lazy, ominous grace. This is not a gentle glow. It is a hungry, oxygen-consuming demon that radiates heat in a 360-degree radius, threatening to ignite every surface it touches simultaneously. The absence of convection also means smoke does not rise. It forms a thick, toxic, blinding haze that simply hangs in the air, stagnating and filling the module, making it impossible to see your own hand in front of your face and hiding the true source and extent of the blaze from the crew. The tools we rely on to fight fire on Earth become nearly useless in this alien environment. A standard carbon dioxide extinguisher, which works by displacing oxygen and smothering the flame, is far less effective. In microgravity, that expelled CO2 doesn't blanket the fire effectively. It can simply form a bubble around it, doing little to cut off the oxygen supply. The fire can continue to burn around the edges of this bubble or even reignite once the gas dissipates. Water mist extinguishers face a similar problem, as the water droplets don't fall and coat the burning material. Instead, they form floating, shimmering globules that are difficult to direct and can short out sensitive electronics, creating new emergencies. The reality of this threat was horrifyingly demonstrated in 1997 aboard the Russian space station Mir. An oxygen-generating candle, a solid fuel chemical canister used to produce breathable air, malfunctioned and burst into flames. It was not a small electrical spark. It was a blowtorch-like jet of fire that shot several feet into the module, filling the compartment with thick, black, noxious smoke. The crew, facing zero visibility and a rapidly spreading blaze, initially struggled to deploy the correct extinguishers. For a few terrifying minutes, the crew reportedly considered the previously unthinkable, abandoning the entire station and evacuating in their Sawyer's lifeboat. They managed to contain and eventually extinguish the fire, but the event left the station's interior coated in a layer of soot, and more importantly, it left the crew psychologically scarred, a stark reminder of how quickly a routine day in space can turn into a fight for survival. Learning from such incidents, NASA and other agencies have made fire safety and research an absolute priority. Scientists conduct controlled combustion experiments aboard the International Space Station, deliberately setting small, contained fires to study their behavior in exquisite detail. They have discovered that materials have a different flammability limit in space. Some things that wouldn't catch fire easily on Earth can burn readily in microgravity. This research has directly led to the development of new, space-adapted firefighting technology. The primary extinguisher used on the ISS now is a water mist system that is precisely engineered to create a finer mist, and crews are equipped with large, powerful fireproof blankets to smother flames manually. Every piece of material on board, from fabric to wire insulation, is rigorously tested for flammability. Emergency drills are constant and exhaustive, with crews training to don oxygen masks within seconds, locate a fire by touch in zero visibility, and work as a seamless team to isolate the module and choke the fire of its oxygen supply. Despite all these preparations, the fear remains. A major fire on a deep space mission, millions of miles from any hope of rescue, represents one of the most immediate and catastrophic failure modes imaginable, a silent, spherical killer waiting in the shadows of the ship. While the void outside threatens with emptiness, the very air astronauts breathe inside their metallic oasis holds its own invisible dangers. We take our atmosphere for granted, a perfectly balanced mix of gases maintained by a planet-wide biological system. In space, that balance is an artificial, high-stakes engineering achievement, a perpetual tightrope walk over a chasm of silent, creeping death. Every breath on a spacecraft is a gift from a complex and fallible machine, and the line between a habitable environment and a toxic one can be breached by a single failed sensor or a tiny leak. The most persistent and insidious threat is the slow, steady accumulation of the very gas we exhale, carbon dioxide. On Earth, plants and ocean algae constantly scrub CO2 from the air, but in a sealed spacecraft it simply builds up. Even at concentrations far below what would cause immediate suffocation, elevated CO2 levels can have debilitating effects. Headaches, lethargy, difficulty concentrating, and impaired cognitive function are all symptoms of CO2 narcosis. For a crew responsible for operating a billion-dollar vehicle and making split-second decisions, a foggy brain isn't just an inconvenience, it's a mission-critical failure. The systems designed to remove this gas, called scrubbers, are mechanical workhorses, but they are not infallible. They can become saturated, malfunction, or simply be overwhelmed if too many people are working in a small space. The terrifying reality of this danger was etched into history during the Apollo 13 mission. The explosion that crippled their service module also damaged the command module's air scrubbers, which were designed to use lithium hydroxide canisters to absorb CO2. The crew was forced to retreat to the lunar module, a spacecraft designed to support 2 people for 2 days, not 3 people for 4 days. The lunar module had its own scrubbers, but they were quickly becoming saturated, and the square canisters were not compatible with the round openings of the command module system. CO2 levels began to rise, approaching dangerously toxic levels. The world watched as engineers on the ground were forced to MacGyver a solution using only the spare parts known to be on the spacecraft: plastic bags, cardboard, tape, and a sock. They devised a makeshift adapter, famously named the mailbox, that allowed the command module canisters to be used in the lunar module. It was a brilliant, desperate fix that saved the crew from being slowly poisoned by their own breath, a stark lesson in the fragility of our life support technology. Beyond the ever-present CO2, the air is under constant assault from a more subtle foe, off-gassing. The interior of a spacecraft is a museum of modern materials, plastics, adhesives, fabrics, and electronics. All of these materials in the warm, enclosed environment slowly release trace amounts of volatile organic compounds, or VOC, into the atmosphere. These are the same chemicals that give a new car its distinctive smell. On Earth, they dissipate into the vast atmosphere. In space, they concentrate. These compounds can range from merely unpleasant odors to genuinely toxic vapors that can irritate eyes and lungs or cause long-term health problems with continuous exposure. The environmental control systems are equipped with activated charcoal filters to trap these pollutants, but the cocktail of chemicals is constantly changing and difficult to fully mitigate. Then there are the more acute and catastrophic leaks. Many spacecraft, including the International Space Station, use ammonia in external loops for their critical cooling systems. Ammonia is a highly efficient coolant, but it is also extremely toxic to humans. A micrometeorite puncture or a faulty valve could allow this gas to seep into the crew cabins. An ammonia leak inside the station would be a nightmare scenario, requiring immediate donning of oxygen masks and potentially a full evacuation of the affected modules. The crew trains relentlessly for such an event, but the margin for error is terrifyingly thin. The air they depend on is a carefully curated mixture, and its purity is maintained by a symphony of machines, any one of which could play a wrong note with disastrous consequences. This invisible battle for clean air is fought every second of every day in orbit, a silent war where defeat is not an option. While we've discussed the threat of larger space debris, there exists an even more pervasive and difficult-to-track menace, a constant, silent rain of tiny projectiles that turn the space around Earth into a cosmic shotgun blast. These are micrometeoroids, naturally occurring particles of rock or metal, often no larger than a grain of sand or a flake of paint, but in the orbital environment, their diminutive size is a terrifying disguise. Traveling at average speeds of 22,000 miles per hour, these specks carry a kinetic punch completely out of proportion to their mass. A 1 millimeter particle, something you might barely feel in your hand, impacts with the energy of a .22 caliber bullet. This isn't a sporadic event. It's a relentless, high-velocity sandblasting that every spacecraft and every spacewalking astronaut must endure. The primary defense against this tiny artillery is a brilliantly simple concept called Whipple shielding, named after its inventor, Fred Whipple. The idea is not to create an impenetrable fortress of a wall, but rather a clever sacrificial buffer. The standard hull of a spacecraft is covered with a thin outer bumper shield, typically made of a material like aluminum or a composite. When a hypervelocity micrometeoroid strikes this outer shield, it doesn't just punch a neat hole. The immense energy of the impact instantly vaporizes the particle itself and a portion of the bumper shield, creating a cloud of superheated gas and molten debris. By the time this expanding cloud reaches the main pressure hull of the spacecraft, its energy and density have been spread over a much wider area, allowing the inner wall to withstand the force without being breached. It's a defense that uses physics against the threat, turning a single, deadly bullet into a manageable puff of gas. The International Space Station is a flagship example of this technology in action. Its modules are protected by hundreds of these Whipple shield panels, and they are constantly taking hits. Astronauts conducting spacewalks often return with reports of small impact craters dotting the station's exterior, a visible testament to the shield's constant work. However, this system has its limits. It is highly effective against particles up to about 1 centimeter in size. Beyond that, the energy of the impact can overwhelm the shielding, and for objects larger than 10 centimeters, the Whipple shield offers little protection, which is why those larger objects are so carefully tracked and avoided. For an astronaut floating outside the relative safety of their ship during a spacewalk, the threat becomes intensely personal. A spacesuit is, in essence, a miniature personal spacecraft, but it cannot be armored with bulky Whipple shields. Its outer layer is a complex blend of materials designed to protect against thermal extremes and radiation, but a direct hit from even a tiny micrometeoroid traveling at orbital velocities could puncture it. A puncture as small as a pinprick would lead to a catastrophic decompression. While suits are designed with multiple layers to help slow such a leak, a significant breach would be a life-threatening emergency with only minutes to get back to the airlock and safety. This is why every spacewalk is a calculated risk, and why crews meticulously inspect their suits before and after each excursion for any signs of impact damage. The risk from these tiny particles is not static. It fluctuates with meteor showers, events like the annual Perseids or Leonids, when Earth's orbit carries it through the debris trail of a comet, can significantly increase the number of particles in space. During these periods, mission planners often reschedule spacewalks and sometimes even adjust the station's attitude to present a more shielded profile to the incoming stream. This constant background risk of micrometeoroid impacts is a sobering reminder that in the vacuum of space, there is no such thing as a truly minor collision. Every single object, no matter how small, is a potential catastrophe waiting to happen, a silent testament to the violent and unforgiving nature of the environment beyond our atmosphere. Beyond the immediate perils of fire and foul air lies a more fundamental, inescapable danger woven into the fabric of the cosmos itself, the relentless pull of gravity. We often think of space as a place of weightlessness, but that's a misleading half-truth. Every single celestial body, a planet, a moon, even a large asteroid, exists at the bottom of what physicists call a gravity well, a conceptual funnel in the fabric of space-time. The larger the mass, the steeper and deeper the well. To travel from one world to another isn't a simple straight-line journey. It's a precarious game of climbing up and sliding down these invisible cosmic slopes, a dance with physics where a single misstep can be fatal. The most tangible danger this presents is the ever-present risk of an unplanned crash landing. This isn't about a pilot error in the traditional sense, it's about the unforgiving precision of orbital mechanics. When a spacecraft approaches a moon or planet, it's not aiming directly at it. Instead, it's executing a carefully calculated trajectory to slip into orbit, a delicate balance between moving forward fast enough to miss the ground and slow enough to be captured by the body's gravity. If the spacecraft's velocity is even slightly too high at the wrong moment, it will simply whip around the planet and be flung back out into space on a new trajectory, an event known as a slingshot maneuver, which is useful when planned but disastrous when not. However, if the velocity is too low, gravity wins. The spacecraft will begin to fall, and without a powerful engine burned to correct the course, that fall will end in a catastrophic impact. There is no atmosphere to use for aerobraking on worlds like the Moon or Mercury. There is only the cold, hard math of velocity and gravity. This leads to the second, equally daunting challenge, the sheer energy required to escape these gravity wells. The concept is called delta V, a term for the change in velocity a spacecraft's engines must provide to accomplish a maneuver. Breaking free of Earth's gravity, for instance, requires a tremendous amount of delta V, which is why rockets are so colossal. They are mostly just fuel tanks strapped to more fuel tanks. But the danger emerges when that fuel is misjudged. The most famous historical near disaster that exemplifies this was the lunar landing of Apollo 11. As Neil Armstrong and Buzz Aldrin descended to the moon's surface, multiple computer alarms blared, forcing Armstrong to take manual control. He expertly guided the lunar module, named Eagle, over a treacherous field of boulders, searching for a safe spot to land. All the while, Mission Control in Houston was silently counting down the remaining seconds of fuel. The landing was so delayed that the Eagle had only about 25 seconds of fuel remaining when it finally touched down. Had Armstrong taken just moments longer, the engine would have cut out and the module would have fallen the final few dozen feet to the lunar surface, likely causing a catastrophic crash that would have stranded them on the moon. That heart-stopping margin of error wasn't due to a leak, but to the immutable laws of orbital mechanics. They had used more delta V than planned to navigate the unforeseen hazards, and they almost didn't have the energy left to complete their mission safely. These calculations become exponentially more complex for missions beyond our Earth-Moon system. To land on Mars, a spacecraft must first slow down to be captured by Mars's gravity, then fire thrusters to adjust its orbit, then fire engines again to deorbit and begin its descent. Each of these maneuvers consumes precious propellant. A miscalculation in any one of them could leave a spacecraft stranded in an unstable orbit around Mars, unable to land and unable to return home, or worse, send it crashing into the red planet below. This isn't theoretical, it's the brutal reality of navigating the solar system. Every mission is a high-wire act performed over an abyss, with the calculations of mathematicians and engineers serving as the only safety net against the immutable and unforgiving pull of gravity. Yet for all the external threats, the gravest danger may ultimately come from within the spacecraft itself, from the catastrophic failure of the very systems designed to keep its occupants alive. A spaceship is an impossibly complex symphony of interdependent machinery, a web of engines, computers, life support, and power systems, all of which must function in perfect harmony. In the unforgiving environment of space, there is no such thing as a minor malfunction. A single faulty valve, a shorted wire, or a crashed computer can trigger a cascade of failures, and with no possibility of a rescue mission or a tow truck for millions of miles, the crew's survival depends entirely on their own ingenuity and the robustness of their backups. Perhaps the most heart-stopping failure is a primary engine malfunction during a critical maneuver. Whether it's the main engine on an Apollo command module firing to leave lunar orbit or the thrusters on a Soyuz capsule aligning for re-entry, these burns are calculated with pinpoint precision. An engine that fails to ignite, cuts off prematurely, or fires erratically can leave a spacecraft stranded in the wrong orbit or on a trajectory that misses Earth entirely. We saw a harrowing preview of this in 1966 with the Gemini 8 mission, flown by Neil Armstrong and David Scott. Shortly after achieving the first ever docking in space, one of their orbital attitude and maneuvering system thrusters stuck in the open position. The spacecraft began to spin violently, accelerating to a full revolution per second, subjecting the astronauts to extreme G-forces and blurring their vision. Armstrong, with incredible coolness under pressure, disengaged the primary system and used the separate re-entry control system to finally stop the spin. They were forced to make an emergency landing, their mission aborted but their lives saved. It was a stark lesson. A single thruster, no larger than a fist, could turn a triumph into a life or death crisis in moments. But the threats are not always so dramatic. A more insidious and constant danger is the loss of electrical power. A spacecraft is a power-hungry entity. Electricity runs the computers, the environmental systems, the communications, and the navigation. This power typically comes from solar panels or fuel cells, and both are vulnerable. Solar panels can be damaged by micrometeoroids, fail to deploy, or simply be unable to generate enough power when in the shadow of a planet or during an unexpected roll. The consequences of a full power loss are unthinkable. The lights go out, the air recyclers stop humming, the computers shut down, and the ship becomes a silent, frozen tomb drifting in the endless night. Even a partial power loss can be crippling, forcing the crew into a desperate game of prioritization, deciding which life-saving system gets the remaining trickle of energy and which must be shut down. Then there is the specter of software and computer failure. Modern spacecraft are flown by millions of lines of code, and a single bug can have catastrophic results. We rely on these systems for everything from managing oxygen levels to calculating engine burn times. A software glitch was responsible for the near disaster during the Apollo 11 lunar descent, overloading the computer and triggering those now famous 1201 and 1202 alarms. A more modern example occurred in 2018 with the Soyuz MS-11 mission. During its climb to orbit, a sensor failed, preventing one of the side boosters from separating cleanly. It crashed back into the core stage, causing a violent decompression and triggering an automatic abort sequence. The spacecraft's computer instantly executed a ballistic re-entry, a much steeper, harder descent that subjects the crew to brutal G-forces. While the system worked as designed and saved the 2 crew members' lives, the event highlighted how a single physical sensor failure could be interpreted by the software as a launch vehicle breakup, initiating a terrifying emergency return. Perhaps the most chilling type of failure is a slow, silent leak, not of air but of a critical coolant like ammonia from the external cooling loops. These systems are the radiators of the spacecraft, rejecting the immense heat generated by electronics and human bodies into the vacuum of space. A micrometeoroid puncture or a fatigued seal can allow this vital fluid to silently vent away. Initially, the crew might not notice anything wrong, but slowly the temperature inside the ship would begin to rise, electronic components would overheat and shut down. The air would become stifling and humid. By the time the alarm bells ring, the situation could already be irreversible, with no way to repair the external leak and no way to stop the ship from transforming into an inescapable oven. This constant, silent reliance on thousands of perfectly functioning components is the hidden anxiety of spaceflight, a reminder that survival hangs by the thinnest of technological threads. But with all of these mechanical threats, we must not forget the most fundamental necessity, sustenance. Every single calorie of food and every drop of water on a long-duration mission must be either brought from Earth or manufactured on the spot. This turns something as simple as a meal into a critical, high-stakes component of survival, where spoilage or contamination isn't just an inconvenience, it's a potential mission ender. You cannot simply open a window to air out a foul smell or run to the store for a replacement. You are utterly dependent on the supplies you have and the systems that preserve them. The challenge of food in space is a multifaceted problem. First, there is the issue of shelf life. Missions to the International Space Station are regularly resupplied by cargo vessels, but a journey to Mars would mean being cut off from Earth for years. All the food must be specially processed, dehydrated, and packaged to last the entire voyage without refrigeration. But even with this advanced preparation, the risk of spoilage is ever present. A single ruptured package, a malfunction in a food warmer, or a tiny breach in sterilization could allow bacteria or mold to take hold. In the confined, recycled air of a spacecraft, such contamination could spread rapidly, potentially leading to food poisoning for the entire crew. An outbreak of nausea, vomiting, or diarrhea in microgravity is more than just miserable. It is dangerously dehydrating and could incapacitate key personnel during a critical mission phase, rendering them unable to perform their duties. This has spurred incredible research into growing fresh food in space. Experiments aboard the ISS, like the veggie system, have successfully cultivated lettuce, radishes, and even peppers. The benefits are psychological as much as nutritional. The joy of caring for a living plant and tasting something fresh is a huge morale booster. But this introduces a new set of dangers. Plants grown in a closed environment can become vectors for mold and pathogens if not meticulously managed. The humidity required for plant growth can also promote the growth of unwanted microbes in the air systems. Every new biological system introduced to the sterile environment of a spacecraft is a potential source of contamination, requiring constant vigilance. The water situation is even more precarious. There are no rivers or lakes to tap into en route. every ounce of water must be rigorously conserved and recycled. The Environmental Control and Life Support System on the ISS is a technological marvel that does just this. It recycles about 90% of the water on board. This includes moisture collected from the air, runoff from washing, and most strikingly, urine. Yes, astronauts drink water that was purified from their own urine and sweat. The process involves advanced filtration, chemical treatment, and distillation to remove contaminants and salts, producing water that is actually purer than most of what we drink on Earth. The terrifying vulnerability of this system is obvious. A failure in the purification process, a chemical imbalance, or a biofilm buildup within the pipes could introduce dangerous pathogens or toxins directly into the crew's drinking water. A waterborne illness would spread through the entire crew with devastating speed. The consequences of such a failure are almost too dire to contemplate, as it would threaten the most basic element of life support. Furthermore, the systems themselves are complex and require regular maintenance. Filters become clogged, sensors can drift out of calibration, and pumps can fail. A major breakdown in the water recycler would force the crew to rely entirely on their emergency reserves, starting a grim countdown timer. On a Mars mission, there would be no possibility of a resupply ship bringing a new pump or a crate of water. A sustained failure could mean the difference between life and death for everyone on board, turning the most essential human need into the most critical point of failure. While we've touched on the horrifying physiological effects of vacuum exposure, the true terror lies in the engineering failures that could trigger it: the sudden, catastrophic loss of pressure that turns a safe haven into a death trap in seconds. This isn't just about the void outside, it's about the fragile barriers we build against it and how the smallest flaw can lead to the most profound disaster. The danger of explosive decompression is a constant specter in spaceflight, a reminder that the difference between life and death is often just the integrity of a seal, the thickness of a hull, or the proper function of a single critical valve. The causes of such an event are as varied as they are frightening. A micrometeoroid, too small to be tracked but traveling at astronomical speeds, could punch a neat, lethal hole through a module's wall. A seal on a hatch or a window, degraded over time by solar radiation and thermal cycling, could develop a hairline crack and fail without warning. Even human error during an airlock cycle, a misaligned handle, an incorrectly sequenced pressurization, could inadvertently open a pathway to the vacuum. The physics are brutally simple. The higher pressure atmosphere inside the spacecraft will violently rush out to equalize with the zero pressure void, creating a hurricane force wind blowing outwards, carrying with it any unsecured objects and, terrifyingly, any crew members not anchored in place. The most tragic and sobering example of this danger is the Soyuz 11 mission. In June of 1971, cosmonauts Georgy Dobrovolsky, Viktor Patsayev, and Vladislav Volkov successfully completed a record-setting 3-week stay aboard the Salyut 1 space station. Their return to Earth began normally with a perfect automated re-entry and landing. But when the recovery team opened the hatch of their descent module, they found all 3 men dead in their seats, their faces calm but marked with dark blue splotches, the telltale signs of hemorrhaging from sudden decompression. The investigation revealed a small pressure equalization valve, located near the crew's seats, had been jolted open prematurely during the separation of the orbital module from the descent module. The valve was supposed to open at a much lower altitude to equalize the cabin pressure with the outside air. Instead, it opened while the spacecraft was still in the vacuum of space. The cabin's atmosphere vented into the void in less than 30 seconds. The cosmonauts who were not wearing pressure suits had no chance of survival. They likely lost consciousness within 15 seconds as the oxygen was pulled from their blood, succumbing to suffocation before their ship ever hit the atmosphere. This single, heartbreaking accident forever changed human spaceflight. The Soviet Union and later Russia, along with NASA and all other space agencies, instituted a mandatory rule. No crew would ever again fly without wearing a pressurized suit during the dynamic phases of launch and re-entry. The Soyuz spacecraft was redesigned to move the valves and ensure such a sequence of events could never happen again. But the lesson of Soyuz 11 echoes through every mission. It is why every hatch on the International Space Station has multiple, redundant sealing mechanisms. It is why crews train relentlessly for decompression emergencies, drilling to locate and isolate a leak by listening for the faint hiss of escaping air and to don emergency oxygen masks within seconds. It is why spacecraft are built with compartmentalization, so a single puncture can be sealed off from the rest of the vessel, sacrificing one module to save the whole. The threat of explosive decompression represents a fundamental paradox of space exploration. We must build vehicles that are strong enough to contain an atmosphere against an infinite nothingness, yet they must also be light enough to be launched from Earth. This constant trade-off between safety and practicality means that every hull is a calculated risk. Engineers use sophisticated models to predict the likelihood of impacts and design accordingly, but they can never reduce the risk to zero. Every creak and groan of a spacecraft structure, every slight drop in pressure registered by a sensor, is met with immediate and intense scrutiny. The memory of those 3 cosmonauts serves as a permanent and solemn reminder that in the relentless environment of space, there is no forgiveness for even the smallest engineering oversight. But while we build layers of protection against the vacuum and radiation, we often overlook the very instrument we rely on to navigate these dangers, our own mind. The human brain is a masterful prediction engine, finely tuned over millennia to interpret the world based on a consistent set of rules: the pull of gravity, the behavior of sound, the horizon line. Take away those fundamental anchors, and the brain's sophisticated software begins to glitch, generating a host of sensory illusions that can mislead, disorient, and even endanger those who trust their own senses. This is the hidden peril of perceptual deception, where the environment of space actively conspires against an astronaut's most basic instincts. One of the most immediate and operationally dangerous illusions is the complete loss of a reliable horizon. On Earth, our inner ear and our eyes work in concert, using the stable horizontal line where sky meets ground to tell us which way is up. In the weightlessness of orbit, that reference vanishes utterly. There is no up or down. An astronaut floating in the center of a module can see a colleague above them, and their brain, desperate for orientation, might suddenly decide that person is right side up and they themselves are upside down. This can trigger a sudden and violent bout of vertigo and nausea, a condition known as space adaptation syndrome that affects roughly half of all space travelers. But the danger goes beyond mere discomfort. During a critical maneuver like docking a spacecraft or manipulating a large robotic arm, a misperception of orientation could lead to a pilot firing a thruster in the exact wrong direction, potentially causing a collision or sending the vehicle into a dangerous spin. This disorientation extends to judging distance and depth. In a familiar environment, our brain uses cues like the relative size of objects and atmospheric haze to gauge how far away something is. Inside the brightly lit, often cluttered confines of a spacecraft with walls only a few feet away, these cues are absent or distorted. An astronaut reaching for a handhold might misjudge the distance, their hand closing on empty air. During a spacewalk, the sheer scale of the environment is overwhelming. The brain struggles to process the distance between the astronaut's boot and a solar array that might be 10 meters away but looks impossibly close against the stark blackness of space. A misjudgment here isn't just an embarrassment. It could lead to a foot making unintended contact with a fragile and critical component, damaging it and jeopardizing the mission. The auditory landscape of space is equally deceptive and ripe for misinterpretation. Sound cannot travel through the vacuum outside, but inside the spacecraft it behaves in strange ways. Without gravity to pull denser, cooler air down, the atmosphere doesn't stratify. This changes how sound propagates, often making it difficult to pinpoint where a noise is coming from. A faint alarm or a worrying hiss might seem to emanate from every direction at once, turning a routine troubleshooting task into a frantic and time-consuming search for a source. The constant, droning hum of life support systems and computers creates a masking background noise, which can either hide a new, critical sound or be misidentified as one. A crew member might become so accustomed to the steady vibration of a pump that when it suddenly shuts down, the resulting silence itself becomes an alarm bell, triggering a rush of anxiety until the cause is confirmed. These illusions are not merely curiosities, they have directly impacted real missions. During the Apollo program, several astronauts reported difficulties while landing on the moon. With no atmosphere to provide haze and with a surface covered in craters of all sizes, they lost all reliable depth perception. The lunar module's shadow provided some clue, but without it, determining whether a crater was 10 feet deep or 100 was nearly impossible. This contributed to the last-second maneuvering that almost exhausted Apollo 11's fuel. Similarly, pilots of the space shuttle sometimes experienced the black hole illusion during night landings. When approaching a runway lit only by a few lights against a completely dark background, the brain can perceive the aircraft as being higher than it actually is, tempting the pilot to dip the nose and descend too early, a potentially catastrophic error. To combat these innate vulnerabilities, space agencies invest heavily in simulation and cross-checking. Spacecraft control panels are designed with tactile and visual diversity, different shaped switches and brightly colored labels to provide unambiguous cues. Pilots are trained to trust their instruments over their gut feelings, a discipline that must become second nature. Crews use constant verbal communication to verify each other's perceptions, a practice called call-outs, where one astronaut will verbally confirm a switch position or a gauge reading that another is about to act upon. It is a relentless, conscious effort to override the brain's ancient, earth-bound programming, a psychological battle fought on every mission to ensure that a simple trick of the light or a misheard sound doesn't become the first link in a chain of events leading to disaster. Encircling our planet like a pair of colossal, invisible tidal waves frozen in space are the Van Allen radiation belts, two donut-shaped zones of intensely energetic charged particles held captive by Earth's magnetic field. This isn't a uniform shell of radiation, it's a structured trap. The inner belt, stretching from roughly 600 to 6,000 kilometers above the Earth, is densely packed with protons accelerated to nearly the speed of light. Beyond that lies a gap, a relatively safer zone, before the far larger outer belt begins, dominated by high-energy electrons that extend out over 50,000 kilometers. These belts are not static, they swell and contract, pulsed by the solar wind, making them a dynamic and unpredictable hazard. The discovery of these zones was one of the first great surprises of the space age. In 1958, America's first successful satellite, Explorer 1, carried a simple Geiger counter designed by Dr. James Van Allen. As the satellite climbed, the instrument readings climbed as expected, then suddenly dropped to zero. At first, it was thought the instrument had failed, but Van Allen correctly interpreted the data. The radiation levels had become so intense they saturated the counter, making it appear dead. Humanity had just discovered that our planet is girdled by a prison of its own making, a cage of radiation that any mission leaving Earth must first pass through. This presented a terrifying problem for the Apollo missions aiming for the moon. How do you send fragile humans through such a destructive environment? The solution was a masterstroke of precision trajectory planning. The belts are thickest around the equator and thin out at the poles. By launching toward the moon on a trajectory that took the spacecraft steeply up through the thinner polar regions of the belts, and by traveling at tremendous speed, engineers minimized the crew's exposure time to just a few hours. The spacecraft's aluminum hull provided some shielding, and the brief transit meant the total radiation dose absorbed by the astronauts was quite low, roughly equivalent to a series of medical CT scans, a risk deemed acceptable for the historic mission. It was a calculated gamble that paid off, a high-speed dash through a gauntlet of invisible fire. However, this danger is making a dramatic comeback with modern plans for a permanent human presence in lunar space. NASA Artemis program and its planned Lunar Gateway, a small space station that will orbit the Moon, face a renewed and far more serious threat from the Van Allen belts. The Gateway's proposed orbit, a highly elliptical path called a near-rectilinear halo orbit, will actually send it repeatedly diving through the very tail of the outer Van Allen belt. Unlike the Apollo astronauts who sped through once, the Gateway and its crew would be subjected to repeated chronic exposure. This changes the risk profile entirely. Prolonged time spent within the belt, even in its outer fringes, would subject astronauts to a significantly higher cumulative dose, increasing their lifetime cancer risk and potentially exposing them to the kind of radiation that can cause acute central nervous system damage or heart disease. Shielding against this is a monumental engineering challenge. The high-energy electrons in the outer belt create a phenomenon called bremsstrahlung, or braking radiation. When these electrons slam into a thick metal shield like aluminum, they don't just stop, they decelerate rapidly and emit powerful X-rays. It's a horrifying trade-off. The very shield you build to protect yourself can become a source of an even more penetrating and dangerous form of radiation inside the habitat. This forces engineers to consider complex, multi-layered shielding using materials like polyethylene, which is rich in hydrogen and better at absorbing radiation without creating secondary waves, or even developing innovative concepts like electromagnetic shields that could deflect the particles altogether. The Van Allen belts, a hurdle cleared by Apollo with a quick sprint, now stand as a persistent and daunting sentinel that must be constantly managed, a reminder that the path to a sustainable future in deep space is paved with the lingering ghosts of Earth's magnetic field. And just as we navigate the visible perils of debris and radiation, a far more subtle and mind-bending danger warps the very fabric of reality itself, a consequence of the universe's fundamental rules that could utterly unravel human connection. This is the bizarre and inescapable reality of time dilation, a direct prediction of Einstein's theory of relativity that tells us time is not the constant, universal tick of a clock we perceive it to be. Instead, it's a fluid, malleable dimension that stretches and compresses based on two things, gravity and velocity. The stronger the gravity or the faster you travel, the more slowly time passes for you relative to someone in a weaker gravitational field or moving at a slower speed. To grasp this, imagine a future mission to a distant star system. The spacecraft accelerates to a significant fraction of the speed of light, say 90%. For the astronauts on board, time feels perfectly normal. Their hearts beat at a regular pace, they age one day at a time, and a mission that they experience as taking 10 years feels like 10 years. But back on Earth, something profoundly different is happening. Because of their incredible velocity, time for them is actually moving more slowly relative to everyone on Earth. When they finally return after their 10-year journey, they might step out of their ship to find that not 10, but 23 years have passed on their home planet. Their children are now older than they are, their parents are gone, and the world they left behind is a distant memory. They haven't just been on a long trip, they have effectively time traveled into the future, becoming permanent strangers in their own time. This effect isn't just theoretical, it's been proven with incredibly precise atomic clocks. Clocks on fast-moving airplanes tick slightly slower than identical clocks on the ground. The GPS satellites we use for navigation orbiting high above Earth, where our planet's gravity is slightly weaker, have to have their clocks constantly corrected for this relativistic effect. If they didn't, the entire system would drift out of accuracy by several miles each day. So for astronauts on the International Space Station, the effect is tiny. They age about 0.005 seconds less than we do every 6 months, but it is undeniably real. The difference is measurable. The terrifying implication for deep space travel is that this effect scales dramatically with speed. The closer you get to the speed of light, the more extreme the time dilation becomes. A voyage to a star 100 light-years away, if undertaken at 99.9% the speed of light, might feel like just a few years for the crew. But by the time they returned, over 200 years would have swept across Earth. They would be archaeological artifacts, living anachronisms returning to a world that has completely moved on without them. Their entire frame of reference culture, technology, social norms rendered obsolete. The psychological toll of this permanent separation is unimaginable. It's the ultimate form of isolation, severing an astronaut not just from their loved ones but from their entire era. The other side of this relativistic coin is gravitational time dilation. Time also slows down the deeper you are in a gravitational well. So, an astronaut orbiting close to a super-dense object like a neutron star would experience time passing much more slowly than a colleague on a ship orbiting farther out. This isn't a hazard we're likely to face soon, but it illustrates the profound and inescapable truth that time is not a universal experience. It is a personal one shaped by your journey through the cosmos. This means that every deep space mission must contend not only with the physical distance traveled, but also with the temporal chasm it opens up. A mission controller sending a message to a ship near Jupiter already faces a delay of over an hour. For a crew experiencing significant time dilation, that delay could stretch into years from their perspective, making real-time guidance and support from Earth an impossible fantasy. They would be truly, utterly alone, adrift not just in space but in time itself. Even with the most advanced technology and rigorous training, the most unpredictable and potentially devastating element in any space mission remains the human mind operating under unimaginable pressure. This is the ever-present danger of human error, not as a simple mistake, but as a complex cascade where fatigue, sensory overload, and the crushing weight of life or death consequences can converge to overwhelm even the most seasoned professional. In the sterile, confined environment of a spacecraft, there is no room for a bad day. Every decision is amplified, every minor slip magnified by the unforgiving physics of space, turning a momentary lapse in judgment into a potential catastrophe. The conditions that breed these errors are baked into the mission profile itself. Astronauts often operate on a severe sleep deficit, their natural circadian rhythms shattered by irregular work cycles and the constant barrage of tasks mandated by a tightly packed schedule. This chronic fatigue directly impairs cognitive function, slowing reaction times, clouding judgment, and eroding the very problem-solving skills they depend on for survival. Compounding this exhaustion is the sheer volume of data they must process. A modern spacecraft cockpit is a symphony of blinking lights, scrolling data streams, and auditory alerts, all demanding immediate attention. In a crisis, this can lead to information saturation, where the brain struggles to prioritize the most critical signals from the cacophony of noise, a phenomenon sometimes called attention tunneling, where focus narrows onto one problem while a more serious one develops unnoticed. The true test of human adaptability under these strains is best understood not through theory, but through the harrowing reality of past missions. The Apollo 13 incident stands as the ultimate case study. When an explosion ripped through their service module, the 3 astronauts and the team on the ground were instantly thrust into a situation for which there was no playbook. They were tired, they were millions of miles from home, and their margins for error had vanished. The response was a masterpiece of improvised problem-solving, but it was born from a series of potential errors narrowly avoided. The famous mailbox fix, rigging a square lithium hydroxide canister to fit a round hole using only spare parts on the ship, required flawless execution under duress. A single miscommunication between the exhausted crew and the sleep-deprived engineers on Earth, a misread manual, or a moment of panic could have doomed the entire effort. Their success was a tribute to human ingenuity, but it also laid bare how perilously close even the best-prepared teams can come to the edge. Conversely, the saga of the Mir space station in the late 1990s illustrates how a relentless series of emergencies can gradually degrade human performance through accumulated stress. The crew faced a devastating fire, a near-fatal collision with a Progress resupply ship, and repeated failures of their primary oxygen generation system. The collision itself was a stark example of a high-stress error. During a manual docking test, the crew, likely affected by fatigue and the complexity of the task, misjudged the approach. The Progress freighter slammed into the station, puncturing a module and sending Mir into a slow spin, requiring a frantic and dangerous effort to stabilize the crippled complex. This period of constant crisis created an environment of sustained anxiety, where the crew was always waiting for the next alarm to sound. This kind of prolonged stress is corrosive, leading to burnout, strained interpersonal relationships, and a heightened probability of mistakes piling on top of mistakes. What these episodes teach us is that the solution to human error isn't to try and eliminate it entirely, an impossible goal, but to build systems that are resilient to it. This is the philosophy of resilience engineering. It involves designing spacecraft with intuitive, fail-safe interfaces that make critical actions deliberate and hard to perform accidentally. It means layering redundancies not just in hardware, but in decision-making processes, mandating that crews cross-verify each other's actions through structured communication protocols. The call-out culture, where every action is verbally confirmed by another crew member, is a direct defense against an individual's momentary lapse. Training now extensively uses high-fidelity simulators that don't just teach procedures. They expose crews to the disorienting stress of multiple, simultaneous failures, inoculating them against the panic that can cloud judgment. The goal is to make the right action the easiest and most intuitive one to take, even when the mind is weary and the alarms are blaring. This acknowledgement of our own inherent fallibility may be the most crucial safety system we ever install. Beyond the dramatic bursts of solar storms lies a more constant, yet equally dangerous stream of energy from our star, the solar wind. This isn't a gentle breeze but a supersonic flood of charged particles, primarily protons and electrons, that flows outward from the sun in all directions, filling the solar system with a turbulent magnetized plasma. For a spacecraft, this creates an invisible environmental hazard that operates on a fundamental level, attacking not the hull or the crew's health directly, but the very electrical integrity of the vehicle itself. The primary danger here is a phenomenon known as spacecraft charging, a silent and insidious process that can lead to catastrophic system failures without any warning. Here's how it works. As this constant wind of charged particles flows past a spacecraft, they interact with its surface materials. Different materials have different properties. Some are good at emitting electrons when struck by the sun's energy, while others are better at collecting them. This can cause parts of the spacecraft to develop different electrical potentials or voltages relative to other parts. Imagine one solar panel developing a strong positive charge while the antenna next to it builds up a strong negative charge. This difference in electrical potential is a recipe for disaster. Nature abhors such an imbalance and will seek to equalize it instantly. The result is a spontaneous electrical arc, a miniature lightning bolt that jumps across the gap between the two components. In the pristine silence of space, these discharges are completely inaudible, but their effects are brutally loud in terms of damage. The consequences of such an arc are multifaceted and severe. The immense heat and energy of the discharge can physically vaporize tiny portions of circuitry, creating pits and flaws in sensitive solar cells, frying delicate sensors and scrambling the data in computer memory banks. This isn't a theoretical risk, it has happened repeatedly. In the early 1980s, NASA, a solar maximum mission satellite, suffered a complete failure of its attitude control system, which was later attributed to an electrical arc caused by spacecraft charging, effectively ending its primary mission until a space shuttle crew could later repair it. These arcs can also generate powerful electromagnetic pulses that radiate through the vehicle's structure, inducing stray currents in wiring that can fool sensors into sending false readings or commanding thrusters to fire unexpectedly. In an environment where a single mistaken command can mean missing a planet or tumbling out of control, this electromagnetic interference is a dire threat to mission success. This hazard becomes exponentially worse during periods of peak solar activity, known as the solar maximum, which occurs on an approximately 11-year cycle. During this active phase, the Sun is covered with more sunspots, and its magnetic field is twisted and complex. This turmoil doesn't just produce more frequent solar flares and coronal mass ejections, it also amplifies the solar wind, making it denser and faster. A spacecraft that might experience manageable levels of charging during a quiet solar minimum can find itself overwhelmed during a maximum. The increased particle flux dramatically accelerates the rate at which charges build up on its surface, turning a manageable background risk into a constant high-stakes emergency. Mission planners for long-duration satellites must account for this entire cycle, designing systems with robust grounding straps, using specially formulated conductive paints on outer surfaces to help equalize charge, and incorporating surge protectors on critical lines. Despite these precautions, the Sun's relentless wind ensures that every vessel sailing the cosmic sea is perpetually at risk of a short, sharp, and silent lightning strike from within. But beyond the technical and physical dangers, we venture into a realm of profound uncertainty where the rules of human society have yet to be written. A domain where a catastrophic failure could leave astronauts utterly alone with no hope of salvation. This is the stark reality of the legal and rescue vacuum in deep space, a chilling frontier where the established protocols of Earth simply vanish. Imagine a critical accident occurring on the first crewed mission to Mars. A medical emergency, a life support failure, or a crippling injury. On Earth or even in orbit, the response is clear. Initiate an emergency return, dispatch a rescue vehicle, or coordinate an international effort. For a crew millions of miles away, these concepts are meaningless. There is no cavalry over the hill. There is no quick return. The journey itself is a multi-year commitment, and turning back is often physically impossible once you've committed to the transfer orbit. The crew would be faced with a terrifying realization: they are completely on their own. This isolation is compounded by a legal landscape that is shockingly underdeveloped, often described as a cosmic Wild West. The foundational treaty, the 1967 Outer Space Treaty, is a noble but vague document. It states that nations are responsible for their national activities in space and are liable for damage caused by their space objects. But it is utterly silent on the gritty, practical realities of a deep space disaster. If a multinational crew is on a mission and a critical decision made by one nation's astronaut leads to the death of another's, which country's laws apply? Who has jurisdiction to investigate? If a commercial company's lander crashes into a rival company's outpost on the moon, causing damage and loss of life, what court hears the case? There are no clear answers. We have no space-based police force, no interstellar ambulance service, and no agreed-upon framework for what constitutes negligence or a crime beyond Earth's orbit. This legal void forces mission planners to confront horrific ethical dilemmas that were once confined to philosophy textbooks and science fiction. The most distressing is the concept of medical and resource triage on a multi-year mission. On Earth, hospitals have triage protocols for mass casualty events, prioritizing care based on who can be saved with the available resources. On a spacecraft, every single resource is finite and irreplaceable: oxygen, water, food, power, and medical supplies. A single crew member suffering a severe, untreatable illness or a debilitating injury could consume a disproportionate amount of these vital reserves in a prolonged attempt to keep them alive, ultimately jeopardizing the entire mission and the lives of everyone else on board. The unthinkable question must be asked: at what point does care become palliative to conserve resources for the surviving crew? And who makes that call? Is it the mission commander, a vote among the crew, a directive from mission control based on cold, hard calculations of consumables? These are decisions no human should have to make, yet they are an inescapable part of the risk calculus for venturing beyond our celestial shore. The concept of abandonment adds another layer of existential dread. The iconic premise of the movie The Martian, where an astronaut is mistakenly left behind, is a dramatization of a very real fear. What if a surface team on Mars cannot make it back to their ascent vehicle? The orbiting mothership, responsible for getting the entire crew home to Earth, would face an impossible choice: risk the lives of everyone by attempting a dangerous and unplanned rescue, or honor the original mission parameters and leave, condemning their colleagues to certain death. Current protocols would almost certainly dictate the latter as the mission's overarching goal. To return the majority of the crew safely would outweigh the tragic loss of a few. This isn't malice, it's the brutal mathematics of survival in an environment where there are no second chances and no margins for error. As we prepare to send humans into this profound isolation, we are not just engineering new machines, we are being forced to draft a new moral code for humanity, one written not in ink but in the stark, unforgiving darkness between worlds. Yet for all the sophisticated threats we engineer against, one of the most persistent and insidious dangers is also the simplest: dust. Not the soft, benign dust of a household bookshelf, but an alien, hyper-abrasive substance that behaves like nothing on Earth. This is lunar regolith, the product of billions of years of meteorite impacts that have pounded the moon's surface without the moderating forces of wind or water erosion. The result is a landscape covered in a fine, glass-like powder where every single grain is a microscopic shard of jagged, sharp-edged glass and mineral, each one possessing the cutting power of a tiny fragment of a broken window pane. The Apollo astronauts were the first to experience just how invasive and problematic this material could be. They reported that it clung to everything: their spacesuits, their tools, the legs of the lunar module, with a bizarre tenacity. It wasn't just dirty, it was destructive. The sharp grains worked their way into the joints of their suits, acting like a fine grit sandpaper that abraded and wore down the critical pressure seals. After just a few moonwalks, the astronauts found their suits' articulated joints, the knees, the wrists, the ankles, had become stiff and difficult to move, their flexibility compromised by the grinding intrusion of this omnipresent powder. Back inside the cramped lunar module, the dust they inadvertently carried in with them filled the air, irritating their eyes and causing a condition the crews dubbed lunar hay fever, with symptoms of sneezing, sore throats, and watery eyes. The smell was described as distinct and unpleasant, like spent gunpowder or wet ashes, a constant sensory reminder of the hostile world just outside their thin metal walls. The threat to machinery is even more acute. This dust doesn't just settle on equipment, it infiltrates it. It can jam moving parts, clog filters, and short-circuit electrical connections by forming a conductive bridge between components. The abrasive nature of the particles means they can quickly degrade the performance of solar panels by scouring their light-sensitive surfaces, gradually reducing their ability to generate power. For any long-term habitat, this presents a never-ending battle. Every airlock cycle, every time an astronaut returns from an excursion, they will bring this contaminant with them. Without a flawless decontamination procedure, the interior of a lunar base would slowly but surely become infiltrated, turning the living quarters into a dusty, hazardous environment. Perhaps the most alarming health risk is to the human respiratory system. The sharp, glassy particles are so fine they can be easily inhaled deep into the lungs. On Earth, our bodies have mechanisms to deal with most dust particles, but lunar dust is a different beast altogether. Its jagged shape makes it difficult for the lungs' cilia to clear, and its chemical composition is reactive, meaning it could potentially cause inflammation and tissue damage far greater than an equivalent amount of Earth dust. Prolonged exposure could lead to a condition similar to silicosis, a debilitating and irreversible lung disease suffered by miners and stonecutters. This means that a simple breath on the moon without rigorous filtration and decontamination could carry a lifetime of health consequences. Adding another bizarre layer to this threat is an unexpected property: electrostatics. On the airless moon, charged particles from the solar wind strike the surface directly, giving the top layer of lunar soil a strong electrical charge. This causes the dust to levitate ever so slightly, making it even more prone to clinging to surfaces. It can create strange, dust-filled hazes or horizon glows observed by the Apollo astronauts, and it guarantees that any surface activity will kick up a stubborn, sticky cloud that is difficult to manage. This ubiquitous, cutting, charged powder is perhaps the ultimate symbol of space's hostility, a seemingly mundane substance that has been transformed by the alien environment into a pervasive, multifaceted menace that threatens both machine and human alike, proving that even the smallest aspects of a new world must be treated with the utmost respect and caution. Imagine a future where the most advanced spacecraft, equipped with the latest technology, suddenly goes dark, not because of a meteoroid impact or a power failure, but because of an invisible, silent attack launched from hundreds or thousands of miles away on Earth. In our increasingly digital and interconnected world, the final frontier has become the newest battlefield for a form of warfare that doesn't use missiles or lasers but bytes and bandwidth. The danger of communication jamming and cyber attacks represents a profound shift in space threats, moving from the environmental and mechanical to the intentionally hostile and digital. At its most basic level, this threat begins with jamming the deliberate transmission of powerful radio signals on the exact frequencies used by a satellite or spacecraft to drown out its legitimate communications. Think of it like trying to have a conversation in a crowded, noisy room where someone has brought a massive amplifier and is blaring static directly into your ear. You can't hear anything else and no one can hear you. For a spacecraft, this loss of signal is catastrophic. A mission control team on Earth would be instantly blinded and deafened, unable to receive telemetry data about the health of the vehicle or send crucial commands. For a crewed mission, this could mean being cut off from all ground-based navigation assistance, medical advice, and emergency instructions, left to float helplessly with no link to home. While often associated with military adversaries testing capabilities, jamming is not just a tool of nation-states. There's a growing concern about the potential for non-state actors or even amateur radio enthusiasts with increasingly powerful and sophisticated equipment to inadvertently or intentionally disrupt critical space operations, turning a vital communications link into a weapon of isolation. Beyond the brute force of jamming lies the more insidious and sophisticated threat of spoofing. This isn't about blocking a signal, it's about hijacking it. A spoofer transmits a counterfeit signal that is designed to be indistinguishable from the real one, tricking the spacecraft's receiver into believing it's authentic. The most terrifying application of this is navigation spoofing. Our spacecraft and much of the technology on Earth relies on the precise timing signals from global navigation satellite systems like GPS. If an adversary can spoof those signals, they could feed a spacecraft deliberately false information about its own position, velocity, and time. Imagine an automated cargo ship bound for the International Space Station receiving spoofed data that convinces its computer it is several miles off course. The autonomous system would then fire its thrusters to correct this false error, inadvertently steering itself onto a collision path with the station or sending it hurtling away into a useless orbit. The crew on the station would see the incoming vehicle deviating from its planned trajectory, but without understanding why, they would have mere minutes to respond to a threat created by a phantom in the machine. The digital vulnerability extends far beyond the radio spectrum and into the very heart of the spacecraft's internal systems. Modern vehicles are no longer purely mechanical marvels. They are flying network servers running on complex software and often designed with connectivity in mind for easier troubleshooting and updates. This creates a devastating potential attack vector, a cyber intrusion from the ground. A skilled hacker or a state-sponsored group could theoretically exploit a vulnerability in the software of a ground control station, use that as a foothold, and then pivot to gain access to the command uplink system. Once inside, they could wreak unimaginable havoc. They could send malicious commands to disable the spacecraft's engines, permanently crippling it. They could shut down life support systems on a crewed vehicle. They could even trigger a deliberate decompression by commanding hatches to open or valves to vent the atmosphere. The 1983 movie War Games depicted a teen hacker nearly starting World War III by breaking into military systems. Today, the same scenario could play out by targeting the infrastructure in space that our modern world depends on for communication, finance, and security. Perhaps the most unnerving aspect of this threat is its deniability and its source. Unlike a missile launch, which can be tracked back to its origin, a cyber attack or a jamming signal can be incredibly difficult to attribute with absolute certainty. An adversary could launch a debilitating attack on a rival nation's satellite and maintain plausible deniability, creating a dangerous incentive for this kind of asymmetric warfare. Furthermore, the attacker doesn't need to be in space themselves. They can be sitting at a computer terminal anywhere on the planet, making space accessible to a whole new class of aggressors. This vulnerability was starkly highlighted in 2008 when hackers reportedly gained access to NAS, a Terra Earth observation satellite, for several minutes, achieving full command capability. While no damage was done, the event served as a terrifying proof of concept, demonstrating that the firewalls separating our terrestrial internet from the celestial commands guiding our spacecraft are not as impenetrable as we might hope. Compounding these human-made threats is a powerful natural one: solar radio bursts. During intense solar flares, the sun doesn't just eject particles, it also unleashes a massive blast of radio noise across a wide spectrum. This natural interference can be so powerful that it completely overwhelms satellite receivers, mimicking the effects of a deliberate jamming attack. For a few minutes or hours, critical communications and GPS signals can be degraded or lost entirely across an entire hemisphere of the Earth. The key difference, of course, is intent. Scientists can usually predict and warn of such solar activity. But the effect on the technology is the same: a sudden, deafening silence where vital data used to flow. This natural vulnerability underscores the fragility of the radio signals we depend on to navigate the void, reminding us that our technological reach into space is tethered by a thread of electromagnetic waves that can be severed by either the fury of our sun or the calculated malice of our own species. And yet, for all the dangers we've mapped and all the threats we've named, the most profound peril of all may be the one we cannot yet see. After 24 known hazards, from radiation to rogue software, we arrive at the ultimate and most humbling danger: the sheer, vast expanse of the unknown. For every risk we can engineer against, there are countless others lurking in the cosmic shadows, phenomena and pitfalls we haven't even begun to imagine. Our journey into the cosmos is not a walk down a well-lit path. It is a step into a profound and ancient darkness, and our flashlight only illuminates the few feet directly in front of us. Consider the bizarre cosmic puzzles that already baffle our brightest minds. Take fast radio bursts, for instance. These are incredibly powerful blasts of radio wave energy that originate from galaxies billions of light years away. They last for mere milliseconds, yet in that flicker they release more energy than our sun does in 80 years. We have detected them, we know they are real, but we have absolutely no idea what causes them. Are they the result of collapsing neutron stars, the signature of immensely powerful alien technology, or something else entirely, something for which we don't even have a name? These bursts are a stark reminder that the universe is capable of generating forces of such immense and concentrated power that they defy our current understanding of physics. What if a future starship, centuries from now, were to wander too close to the source of one of these events? The consequences are utterly unknowable. Our own solar system, which we think we know, is still filled with potential surprises. We've sent probes to many worlds, but we've only scratched the surface, literally. What hidden dangers lie beneath the icy crust of Jupiter's moon Europa, or within the methane lakes of Saturn's Titan? Could there be unforeseen geological phenomena like cryovolcanoes that erupt with supercooled liquids instead of lava, creating unpredictable and hazardous terrain? Or consider the uncharted wilderness of the asteroid belt. While we worry about catalogue debris, what about the possibility of previously undetected clouds of ultra-fine dust or pockets of strange, reactive gases lingering in the orbits of these ancient rocks? A spacecraft passing through such a region could find its sensors blinded, its solar panels coated, or its hull subjected to a type of chemical erosion we never planned for. Then there are the biological unknowns, the long-term effects we cannot possibly predict from our short stays in low Earth orbit. What does a multi-year journey, spent entirely outside the protective cocoon of Earth's magnetosphere, do to the human microbiome, the trillions of bacteria essential to our digestion and immune system? Could radiation and microgravity trigger unforeseen genetic mutations that only manifest after years, or even in the children of astronauts conceived in space? We are essentially running a decades-long experiment on human biology in real time, with a sample size of a few dozen individuals. The data is precious, but it is also terrifyingly incomplete. The first crew to spend 5 years traveling to another star system might return physically unharmed but fundamentally changed in ways we cannot yet diagnose. This ultimate danger, the unknown, is not a failure of our science, it is its very essence. It is the reason for caution, for redundancy, for the humble admission that our knowledge is and may always be provisional. The greatest preparedness is not to assume we have thought of everything, but to build systems and crews that are resilient, adaptable, and intelligent enough to face the thing they did not see coming. It is the understanding that the final and most important item on any list of space dangers will always be a blank line, reserved for the threat we haven't met yet, a silent testament to the fact that the universe will always have secrets to reveal, sometimes in the most dramatic and challenging ways imaginable. And so we reach the end of our journey through the cosmos's darkest corners, having faced 25 silent specters that turn the final frontier from a realm of wonder into a gauntlet of existential risk. These are not the fabricated terrors of science fiction, but the sober, meticulously documented conclusions of physicists, physicians, and engineers. Each one represents a monumental puzzle that must be solved not with fantasy, but with courage, innovation, and an unflinching respect for the laws of physics. From the subatomic violence of cosmic radiation to the profound psychological weight of absolute isolation, from the hypervelocity sting of a micrometeoroid to the slow, insidious decay of the human body in microgravity, every mission beyond our atmosphere is a testament to our willingness to face these dangers down. This monumental effort, this balancing act on the edge of impossibility, is what truly defines the heroism of exploration. It's a courage that goes beyond a single moment of bravery. It is the courage to commit to years of training, to place your trust in countless layers of technology, and to say yes to a journey where the margin for error is absolute zero. It's the quiet courage of the engineers who double-check every line of code, the doctors who study the long-term effects of radiation, and the astronauts who understand the full weight of every risk as they strap themselves to a controlled explosion, heading for an environment that offers no second chances. Our ventures into space represent humanity at its most bold and its most vulnerable, a species of fragile biological beings using the full force of its intellect to reach beyond its cradle. Now we turn the conversation over to you. After delving into these 25 hidden dangers, which one truly captured your imagination and sent a chill down your spine? Was it the silent, creeping threat of cosmic radiation that could end our interplanetary dreams? The terrifying reality of explosive decompression and the memory of Soyuz 11? Or perhaps the psychological abyss of deep space isolation, knowing you might return to a world that has moved on without you? Share your thoughts in the comments below. We're genuinely curious to hear which cosmic peril resonates the most. If this journey into the unknown has captivated you, make sure to subscribe and hit the notification bell. Our channel is your launchpad to unraveling the universe's greatest mysteries, from the black holes that warp reality to the ancient secrets hidden on distant worlds. The final frontier is vast, and its stories are just